Well, hello, ap1. This is our second video. We're starting on page 441 of your textbook, starting with section 13.7, waves. Basically, we're going to learn two different types of waves and some properties of those waves. So, the two different types of waves we want to talk about are going to be a transverse wave and a longitudinal wave. A transverse wave and a longitudinal wave. So, we want to look at something called transverse. A transverse wave is a wave in which the amplitude is perpendicular to the velocity. The amplitude is perpendicular to the velocity. The other type of wave we have is a longitudinal wave. A longitudinal wave is one in which the amplitude is parallel or antiparallel to the velocity. So what does all this mean? Well, you guys would have a lot better chance of understanding this if you knew what amplitude was. Amplitude, remember, is the amount that we've oscillated away from some equilibrium point. So a wave oscillates away from equilibrium some amount. In a transverse wave, this oscillation is perpendicular to the traveling direction of the wave. For a longitudinal wave, this amplitude, this oscillation is parallel or antiparallel to the velocity of the wave. Let's see if I should make this look a little clearer. Let's see, here is an example of a transverse wave. Notice the wave travels to the right, but it actually oscillates in the vertical direction. So it's oscillating up and down, but the wave is traveling to the right. The amplitude of oscillation is perpendicular to the velocity. Okay? And for a longitudinal wave, notice the wave compresses and stretches, so the amplitude of oscillation is to the right and to the left, forward and backward. The velocity of the wave is to the right. So the amplitude of oscillation is parallel or antiparallel to the travel of velocity, to the direction of the velocity. All right, cool. So let's get out of this video and back here. So waves are transverse or longitudinal. Now, for our examples, I'm going to draw transverse waves. There's no way I'm going to even attempt to draw a longitudinal wave. But we have our equilibrium point. The wave oscillates above and below that equilibrium point. This would be the amplitude of oscillation. That would be our amplitude, how far away from equilibrium. It can happen in the positive and negative direction. That's our amplitude. Our wavelength is the distance from one crest to another crest. That is wavelength. We will use the Greek letter lambda. You can think of lambda as the front half of a giraffe, if you like. Being silly. Lambda, wavelength. This wave would be propagating, for example, if we wanted to look at it. This wave would propagate with some velocity to the right, say. So I've got a wave, it's a transverse wave, it's oscillating vertically with some amplitude. It's got a wavelength, crest to crest, and it's got some velocity. This will also oscillate. This wave will also oscillate with some frequency. And the frequency, remember, is just going to be in hertz, and frequency is the number of cycles per second. How many times does it oscillate up and down per second? Okay? Well, frequency is hertz, which is, like I said, inverse seconds. Wavelength is measured in meters. Well, if you combine wavelength and frequency, you would get meters per second. So as it turns out, velocities of a wave can always be determined as the wavelength times the frequency. Meters times per seconds. Meters per second. We get our velocity. Woohoo! All right, moving on. Back to our textbook. And here's the part of your textbook that outlines the things I just described. If we go to page 445, you see example 13.8, a traveling wave. I'm not actually going to do this problem at this point. You guys should be able to handle this one. Go through the example. It's laid out for you, pretty straightforward. Once you've got comfortable with that, attempt exercise 13.8. And then move on. Example 13.9 on page 445. Again, I'm not going to solve this one out right here. This one's laid out for you fairly well. Go through that example when you're comfortable. Go through the exercise. If you have trouble with these, again, this is something we can ask about in the future. I'm going to move on to section 13.9, the speed of waves in a string. So this is going to lead us to something like a guitar, for example, which is something that might come up later. But imagine in this case we're trying to send a wave, most likely a transverse wave, down a string, like I said, a guitar string maybe, and we want to determine the velocity. Well, as you can see, equation 13.18 outlines that velocity, and it says that the velocity of a wave in a string is equal to force, mu, and square root. We've seen the Greek letter mu before. In this context, the Greek letter mu is going to be the mass per unit length of the string. So we have some string. It's going to have some mass per unit length, mu, and that mu is going to be the mass of the string divided by the length of the string. That gives you mu, the linear density if you want to call it. F, that's just the force in the string. The force in a string is just tension. That's what we've called it before, the tension in the string. So the velocity in a string is just going to be the ratio of the tension in the string, how tight is the string, divided by its linear density, the mass per unit length, and then square root it. That gives us the velocity of a wave in a string. Okay? If we go back to our textbook, and I'll see if I can find it. If we go back to our textbook, we will see on page 447, interactive example 1310. They want to find a pulse traveling in a string. So if you look at the picture, we've got a string with a mass and a pulley. The mass is dangling off the pulley, and that's going to put some tension in that string. A wave can be generated in that string, or a pulse can be generated in that string, and it will travel at some velocity because there is some tension in that string. The problem says a uniform string has a mass of 0.03 kilograms and a length of 6 meters. That mass and that length can be combined to give you mu. Okay? That mass and that length can be combined to give you mu. Okay? They say find the speed of a transverse wave pulse in that string. Okay? Well, the velocity is going to be the force divided by the mass per unit length. Mu is the mass per unit length. They told you the 0.03 kilograms and the 6 meters. For the tension in the string, well, you just got to look at a free body diagram. There is the mass dangling from the pulley. There's going to be some force upwards, and there's going to be some force of gravity downwards. Remember, this is the mass dangling off the pulley. There's no acceleration in this case. So that means that the force is just going to equal mg. The tension in the string is just going to be the weight of the mass. That mass right there, that one is the one that was 2 kilograms. Okay? And g is 9.8. So if we take those two things, we can use the force and the velocity to find the force and the linear density, mass per unit length, to find the velocity. Okay, I think that should be enough of a hint to get you through that problem. Go through that problem, and then when you're done with it, try exercise 1310. So at this point, you should be able to do 13.8, 13.9, and 13.10. That concludes this chapter as far as I can see. As far as I can tell, we should still plan on having your homework due on Friday the 27th. I'm going to go to Shobi and change the deadline there, so it should be due later in the day, but I still want that homework turned in Friday. We'll call it good. See you next time.